Alright, so in this video we're going to close out our discussion of different types of plate boundaries by looking at transform margins. So what you should take away from this video is the ability to identify transform margins in the ocean and on land, and then to identify how transform margins can change over time. This is key because they're really kind of the connective tissue that holds all of plate tectonics together. Transform margins can also generate enormously powerful earthquakes, and so we're going to talk about where the energy from these earthquakes really comes from. Okay, so this last type of margin, this transform margin, it's also sometimes called a conservative margin because no crust is created or destroyed. This is pieces of crust, these are different plates sliding past each other. So this produces many strong shallow earthquakes because there's a lot of friction caught up in between these segments of plates right at the boundaries. But it's not enough energy to create temperature that would melt anything, so there's not volcanic activity happening at these transform boundaries. It's just earthquakes. Although just earthquakes is probably not much solace to anyone who has to suffer the effects of them. So these are often happening in the ocean at an oceanic transform boundary. These are often happening at ocean ridges and spreading centers. And this is what's generating these large fracture zones that can be seen on the bottom of the ocean floor. For example, the Mendocino Fault or the Clipperton Fault that runs basically from North America out into the center of the Pacific. So here's what a transform fault looks like in a region of ocean spreading. This is the northern end of the East Pacific Rise. The East Pacific Rise sort of terminates right in Baja California. It's not like the Mid-Atlantic Ridge, which goes all the way up through the margin. So you can see overall that the North American plate is heading in this down and right direction, this southeast direction, and then the Pacific plate is heading northwest. And so overall you can see the spreading centers are aligned with this, or they're in fact helping to push the Pacific plate in this northwest direction and push the North American plate down here. But there's this offset here. It's not a straight line of spreading centers. There's segments where there's continual spreading, and then there are these transform faults here. So the transform fault is really put in place so that, or it emerges because there's two pieces of crust that are going in opposite directions here. So for instance, if you look at this spreading center here, this part of the crust is being pushed this way, this part of the crust is being pushed this way. So because you have things sliding past each other, there is a transform fault that emerges, and earthquakes can be generated there. The more famous transform boundaries are usually on land. So for instance, the San Andreas Fault that runs basically from the tip of Baja California and connects this East Pacific Rise to the Juan de Fuca Plate and the spreading center over here. So this runs through Southern California, up through San Francisco, and then over here where there's a subduction zone that's where oceanic crust is being pushed underneath North America. This is where you have volcanic activity in the Cascade Range. So if you're flying over Southern California, sometimes you could spot this from a plane. Usually there's not a lot of clouds. And this is the San Andreas Fault. On one side there's the North American plate, on the other side the Pacific plate, and these are being subject to forces that are continuous for pushing past one another. But even though the forces that are sort of charging this fault are continuous, the slip is intermittent. So this is what's called a slip strike earthquake or fault type. Essentially you have this energy being stored up, and then it's released through a large earthquake that results in movement of the plate along the fault. So unfortunately San Francisco right over here lies right on the San Andreas Fault as it passes through Northern California here. Again, North American plate is headed in this direction, the Pacific plate is headed this direction. And when this fault releases energy, this results in giant earthquakes like the 1989 earthquake in San Francisco that happened during the World Series. You can see how it totally destroyed this highway and cut it into segments. These are really damaging earthquakes. They're huge hazards, and so this is just something that is a fact of life in coastal California where you live on the San Andreas Fault. So it's important to recognize that these transform faults, sometimes they don't get their day in the sun, but they're the really important connective tissue between between different types of plate margins. We mentioned before how you go from a spreading center in the East Pacific Rise to a subduction zone up north in the Cascade region. And so in order to connect a spreading center with the subduction zone, you need something that's going to allow motion to slide alongside. That's the transform boundary that allows the Pacific plate to sort of slide to the northwest and the American plate to slide to the southeast. So we mentioned before how it's kind of odd that the East Pacific rise, despite the fact that it's the fastest spreading center, it's not actually evenly spaced throughout the Pacific region like the North Atlantic or like the Mid-Atlantic ridge is. And actually, this is something that only emerged pretty recently. Back around 80 million years ago, there was this spreading center that went all the way up from the center of the Pacific all the way through the North Pacific. This is what North America looked like at the time. You can see there's a lot of the exotic terrains that form Alaska haven't actually collided yet. And this is a spreading center, so you're going to be forcing material over here and forcing material over here. The Pacific plate is going to go to the left. This is actually what's called the Farallon plate. This is a plate that doesn't exist anymore, going to the right. And what's essentially happening here, this is during the later stages of the breakup of Pangaea, North America is moving to the right, and it's actually just going to consume this spreading center. So not only is this plate going to be eaten, this East Pacific rise is going to be totally subducted underneath California. And then you have this transform boundary, the San Andreas Fault, emerging in its stead, because you have parts of the East Pacific rise that are still spreading, and you also have the subduction zone over here that's still active in the Cascades. So these transform boundaries are really essential to connecting a subduction zone with a divergent boundary, because they can't really actually meet. So essentially what you have here is plate tectonics that are out of balance. There's more consumption of oceanic crust in subduction zones than there is production at the mid-ocean ridges. This causes the whole ridge to slide towards North America and subduct under California. This terminates the subduction zone in California and creates the San Andreas Fault. So this is just an annotated version of the video we just saw. So originally there was this Farallon plate, similar to the Juan de Fuca plate up in the northwest, and actually parts of the Juan de Fuca plate used to be what's called this Farallon plate. So you have spreading here that's pushing new crust towards California, and you have subduction of that oceanic crust below California. And this leads to volcanoes all across the North American West Coast, even in areas where there aren't active volcanoes currently today. The reason there aren't volcanoes currently today is because this whole mid-ocean ridge gets subducted underneath this North American plate. You still have East Pacific rise sort of spreading over here to the south. It's forming the Cocos plate, and then that gets subducted underneath Mexico, where there's still volcanic activity today. You have the Juan de Fuca plate that's powering the Cascade volcanoes over here. And to connect them, you have the San Andreas Fault that's sort of sliding the Pacific plate up here to the northwest and allowing the American plate to slide down to the southeast. Mountain regions like the Sierra Nevada here, these are relics of granites that were formed when California had this active subduction going on that was allowing new crust to be formed. So even though there's no subduction on the west coast of the U.S. Near California today, a lot of the crust that we have here and a lot of the really prominent mountains were formed during that time. And actually you can see this sort of zombie Farallon plate beneath the U.S. in these seismic images. This is a plate that was subducted and has since broken off and sort of just hanging out underneath continental U.S. today. So the San Andreas is usually the most famous, large fault system on land, but it's not the only one. The Alpine Fault in New Zealand is responsible for several large earthquakes there. That's a transform boundary. There's also several ones in Haiti and Turkey, in sort of Venezuela region and elsewhere in Tonga. These are areas where there's lots of, there can be really strong earthquakes because there's so much energy stored stored up in these transform boundaries that are released during large earthquakes. So the ultimate drivers for this energy is the motion of the plates. It's because the plates are moving in certain ways, and in order to slide past another, energy is stored up and then released. So what's driving the motion of the plates? We can think about this as three mechanisms overall. We talked about slab pull already. This is basically what happens when the subducting oceanic crust becomes more dense because the lighter elements, the volatiles, are turning into a magma and joining the overlying crust or island arc. the resulting slab gets more dense. It's more dense than the mantle, so it sinks down into the mantle. And as it does so, it's pulling the rest of the plate along with it, and then that's creating a drive for more spreading here. In addition to slab pull, there's sort of classic mantle convection here. This is because there's buoyant parts of the mantle that are rising up in spreading centers. They're diverging to the left and to the right, and they're helping to drag the plate along with it, and that's helping to increase spreading as well. And lastly, there's this phenomenon called ridge push. This is basically the consequence of a mid-ocean ridge that's held up 2,000 meters above the sort of standard abyssal plains. Because this is, is much higher than the rest of the ocean floor, it's going to be pushing down and it's going to be pushing out, and there's going to be a sideways component of that force that's going to help push the mantle along too. So these are three forces that are contributing to the motion of plates today that are leading to earthquakes in transform margins. All three of them originally stem from this fact that there's a large heat gradient from Earth's core out to Earth's surface. But in addition to that table, when you're reviewing this material, make sure you can identify transform margins in the ocean and on land, and explain how transform margins can evolve over time. These transform margins are sources for large earthquakes, but identify where that energy originally comes from. It's from this heat gradient on Earth between the hot lower mantle and the cold surface of the Earth, and those gradients are turned into gravitational energy through slab pull, ridge push, and mantle convection that help pull plates apart and send plates off in different directions.